Okay guys, so today we're going to start talking about trig equations. And the first thing that I need to tell you, I suppose, is what a trig equation is. A trigonometric equation is just an equation involving a trig function. No surprise, right? So something like this, sine of x is equal to 1/2. That's an equation with a trig function, so that's a trig equation. Obviously they can be more complicated, something like tan squared of 2x plus pi equals root 3 over 3. That is also a trig equation. And the goal, of course, is to find the solutions. In other words, we need to find the values of, in this case, x, which satisfy the equation. Before we can do this, before I tell you how to solve trig equations, we really need to take a brief detour and talk about coterminal angles. Okay, so let's think about coterminal angles for just a second. So here's a question. What are the angles coterminal, and I'll remind you what that means in a moment. What are the angles coterminal with 45 degrees? So if you remember, 45 degrees, coterminal just means angles which sit in the same location on the unit circle, right? So if I have a unit circle like this, 45 degrees is right here, that's 45 degrees. Any other angle which sits in this same location would be coterminal with 45. And if you remember, the way to obtain coterminal angles is basically to just add and subtract full rotations. If you're in degrees, as I am right now, that would be adding 360 degrees. So if I add 360 degrees to 45, that's just going to bring me all the way around. That angle is going to be sitting in the same place, so that's going to be coterminal. So if I took 45 degrees and I added 360 degrees, that would give me 405 degrees. So this angle right here is coterminal with 45 degrees. They both sit in this same location. But what I want to point out is that you could add 360 degrees again, right? You could add 2 copies of 360 degrees. That would just be adding 2 full rotations to 45, and that also would be coterminal. And that happens to be 765. And why stop at 2 full rotations, right? We could just as well add 3 copies of 360, right? We could add 3 full rotations to this angle, and it would be sitting in the same place, and that happens to be 1125 degrees, okay? Now what I want you to notice is the similarity between these expressions, 45 plus 360, 45 plus 360 times 2. There's a lot of similar structure in these expressions. And the goal that I want to accomplish here is I want to come up with an algebraic expression which represents the coterminal angles. Okay, as you can see, there are infinitely many coterminal angles, right? We could keep adding 360 as many times as we wanted. What I want really is a formula. I want an algebraic representation of all those infinitely many coterminal angles, and the way you do it is sort of lurking in these expressions here. One thing I'd point out is that 360 in this expression could be written as 360 times 1. And, you know, I'm kind of missing something. You know, 45 degrees, this is kind of dumb, but 45 degrees is coterminal with itself, right? Like 45 degrees sits in the same location as itself. So therefore, I should include 45 on this list. How would I write 45 as 45 plus 360 times something? Well, it would be 45 plus 360 times 0. So that would be 45, okay? Now, you might remember that you are also allowed to subtract full rotations, right? You're allowed to subtract 360 degrees from your initial angle, and that will produce also coterminal angles, right? Like if I take 45 degrees and I subtract 360, that would give me negative 315, I think, right? If I subtracted 360 degrees, well, how would I write that? I could write it as minus 360, but I'd like to write it in the same way that I wrote these guys. I can write plus 360 times negative 1, and that is subtracting 360. So the point here, and you can subtract another copy of 360, and that would just be 360 times negative 2, right, equals something. So here's my point, okay? All of the angles coterminal with 45 look like this. They are of the form and this is the big reveal, they're all of the form 45 plus 360 times some integer n, okay? N could be -2, -1, 0, +1, +2, all the way out, okay? And we don't really need these parentheses here. It's easier to just write 45 plus 360n. So this expression here represents all infinitely many angles coterminal with 45 degrees, okay? That's if you're measuring in degrees, right? And it's important to recognize that n has to range over all the integers. That includes, the negative numbers, right? 0, 1, 2, and so on. Okay, so that's the idea. Now, if you were to do this in radians, it's very similar. If you were to, so suppose I asked you, what are all of the angles coterminal with, say, pi over 3, right? That's a different angle. In radians, what are the angles coterminal with that? Well, I could do pi over 3 plus 2 pi. That would be coterminal. Or I could add 2 copies of 2 pi, or I could add 3 copies of 2 pi, or I could add 4 copies of 2 pi, and I could also do negative, right? I could subtract copies of 2 pi, I could do like -2. So in general, the angles coterminal with pi over 3 in radians would be pi over 3 plus 2 pi n, where n is an integer, so negative, all the way from negative infinity, right? -2, -1, 0, 1, 2, and so on, okay? So the big idea here, and that was kind of a detailed explanation, but the main takeaway here is that if you need to represent all angles coterminal with a certain angle, then what you have to do is the following. So if theta is an angle in degrees, then the set of all coterminal angles is given by theta plus 360n, okay, where n is an integer. On the other hand, if your angle is measured in radians, so if it's measured in radians, which it usually will be, if it's measured in radians, then it will be theta plus 2 pi n, okay, again where n is an integer. Okay, so that's a detour on coterminal angles, and you're going to see why that's really important in a moment. So, of course, the lesson here today is to solve trigonometric equations, and I haven't told you how to do that yet, but here's the idea. Let's start with an example. Here's my example. It's sine theta is equal to √2 over 2, okay? This is a trigonometric equation, and the goal is to find all the solutions. That means we need to find all of the angles, theta, which satisfy this equation. That means we need to find all of the angles which have a sine of √2, right? That's what we need to do. So if we take a look at the unit circle, here's, a copy of the top half of the unit circle. We can right away identify one angle as having a sine that is a y-coordinate of √2 over 2. That would be pi over 4, right? So certainly theta equals pi over 4 is a solution because that angle has a sine of √2 over 2. But the crucial thing to recognize is that any other angle coterminal with pi over 4 would also have a sine of √2 over 2, wouldn't it? Like if I take pi over 4 and I add 2 pi, that's going to be sitting right here as well, and it will also have a y-coordinate of √2 over 2. Therefore, not only is pi over 4 a solution to this equation, but actually any angle coterminal with pi over 4 will also be a solution to this equation. Therefore, writing pi over 4 is not enough. That's not all the solutions. Okay? I need to include all of the angles coterminal with pi over 4. And remember, we just figured out how to do that algebraically. The collection, the set of angles coterminal with pi over 4 is given by pi over 4 plus 2 pi n, where n ranges from -3, -2, all the integers, right? So this single formula actually represents an infinite number of different angles, one angle for every integer value of n. And so right away we see this equation actually has an infinite number of solutions, right? Which is pretty crazy. But actually this isn't even all the solutions, because if you go back to the unit circle, there's another angle on here which has a sign, a y-coordinate of root 2 over 2. That would be this one over here, 3 pi over 4. This angle also has a y-coordinate of root 2 over 2. So we need to include that as well. And that's not included in our current list, right? This expression here only represents the angles which sit at pi over 4. This is a new guy. So what I'm going to do is I'm going to write, okay, well, theta could also be 3 pi over 4. But then by the same argument that I just made, any angle coterminal with 3 pi over 4 would also be a solution. So I need to include all of those guys. So what I do to represent all of those guys simultaneously is I take 3 pi over 4 and I write plus 2 pi n. Okay, so really the total solution set to this equation is represented by these two formulas, right? For every integer value of n, each of these formulas gives us a solution. Yeah, so there are infinitely many solutions, right? Okay, so that's basically how that works. And just some terminology, this solution here and this solution here, the solutions that we read from the unit circle directly are what I call base solutions. Okay, these two guys here, these are called base solutions. And it's a little bit like your base solutions generate the entire solution set by adding copies of full rotations, by adding copies of 2 pi if you're in radians. So the way to solve trigonometric equations basically goes like this. You identify your base solutions, that's the solutions on the unit circle, and then you slap on 2 pi n to account for the fact that any angle coterminal with those base solutions would also work, okay? So let's maybe just do another example. Suppose I wanted you to solve the equation cosine theta is equal to 1/2. So how does that work? Well, you go to your unit circle and you look for the angles which have a cosine of 1/2. So certainly pi over 3 is a solution because its x-coordinate is 1/2. That is one base solution. Okay, that's my first base solution. Usually you need two base solutions, okay? There's another angle on the unit circle which also has a cosine of 1/2. It's not on this unit circle because it's only printed half of it. The other angle which has a cosine of 1/2 would be down here. That would be 5 pi over 3, right? 5 pi over 3 would also have a cosine of 1/2. That's the other 5 pi over 3. Those are my two base solutions. But then to get the total solution set, right? There's an infinite number of solutions in reality. To get the total solution set, what I have to do is add n to each of these two base solutions. And then these two formulas represent or encapsulate all infinitely many of the solutions to this equation, right? If you actually want to know what some of those solutions look like, you just have to pick specific values for n, right? If you replace n with 0, you get the two base solutions. If you replace n with 1, then you get something else. If you replace n with 2, you get something else. And n can be negative as well, right? Okay, so that's solving trigonometric equations. Basically, you just look at your unit circle to get your base solutions, and then you slap on 2 pi n for each one, right? Assuming you're in radians. If you're in degrees, it would be 360 n. Okay, so there's just one more thing to talk about, and in general, trigonometric equations can be, a little bit more complicated, perhaps than the ones that I've done so far. Let's consider this one: root 2 minus 2 sine of x equals 0. Now, what's different about this trig equation? Well, basically, the trigonometric function, the sine function, isn't isolated. That's what's different about this equation. So your first move when solving trigonometric equations is, if you have to, isolate the trig function, right? Get the sine x by itself. So how would we do that? Well, I think we would subtract the root 2 from both sides. That gives me this. And then divide both sides by -2. That gives me sine x equals positive root 2 over 2. I think we actually already solved this equation, didn't we? This is exactly the equation we did in the first example. The base solutions are going to be pi over 4 and 3 pi over 4. But then to get all the angles coterminal with those two guys, we slap on a 2 pi n to each one of them. Okay, so those are the solutions. Let's do a little bit more of a harder one, and this will be the last example that I do in the video. Let's consider something like 2 cosine squared of x is equal to 1. All right, so again, before you can apply the argument that we just went through about like base solutions and coterminal angles, what you really have to do is get the trig function by itself. So remember what this notation really means, like the square here. What's really being squared is the cosine function. So maybe a more clear way of writing this would be cosine of x quantity squared, right? I think that makes it a bit more obvious how you're supposed to get the cosine by itself. So how are we going to get the cosine by itself? Start by dividing both sides by 2, right? So that's like this equals 1/2. And then I have to take the square root of both sides, right? Now, the thing is, if I take the square root of both sides, remember, I have to write a plus minus, right? So plus or minus root 1/2. This, by the way, the root 1/2 can be simplified. That's the same thing as, you know, the square root of a fraction is just the square root of the top over the square root of the bottom. But of course, root 1 is just 1, so that's 1 over root 2. And if you rationalize this by multiplying top and bottom by root 2, you get root 2 over 2. That's important because root 2 over 2 is a unit circle value that we recognize, whereas like root 1/2 is not really. Okay, so ultimately what we're told here is that cosine of x is equal to plus or minus root 2 over 2. I'll just rewrite that here for clarity. Cosine of x is equal to plus or minus root 2 over 2. This is actually 2 separate trigonometric equations. 2 different equations because of the plus or minus. One for plus and one for minus. So what this is really telling you is cosine of x could be positive root 2 over 2. That's one equation. Or cosine of x could be negative root 2 over 2. That's the minus sign. And you have to just solve these 2 equations separately. Okay, so let's do it. So cosine x is equal to root 2 over 2. What are my base solutions? Well, the angles on the unit circle, which have a cosine of root 2 over 2, are pi over 4. That's one of them. And the other one is, it's the one in the 4th quadrant. That'd be 7 pi over 4. But then I need to include all the angles coterminal with those 2 angles. So I have to slap on 2 pi n to each of those, right? Okay, so those 2 formulas represent a bunch of solutions. But then I also have to solve this equation, right? So what are my base solutions? What are the angles which have a cosine of negative root 2 over 2 on the unit circle? Well, one of them is 3 pi over 4, and then the other one is 5 pi over 4. Okay, but then, of course, I need to account for all the angles coterminal with those 2 base solutions, so I have to slap on a 2 pi n to each one of them. So the total solution set to this equation is very large, right? There's a lot of solutions, and the algebraic representation of all those infinitely many solutions is given by these 4 formulas, right? Each one of these formulas gives you a different solution for every integer value of n, right? That's a lot of solutions. So in summary, solving trigonometric equations, basically you just you isolate the trigonometric function if you have to, right? Get the cosine by itself or the sine by itself or whatever. And then you look at your unit circle, or hopefully you have it memorized, and you think about your base solutions. And then to account for the fact that any angle coterminal with those base solutions is also a solution, you got to slap on the 2 pi n at the end, if you're in radians.